In this video, we're going to talk about 7.1, which are eigenvalues and eigenvectors, and we'll talk a little bit about eigenspaces as well. But the topic here is eigenvalues and eigenvectors. Let's talk about what that means. That if we have a matrix A, that we want to find solutions to the equation A and then times the vector x. So this transformation that we were talking about in previous sections where t of x is equal to ax, we want that to be equal to some real number lambda times our original x. So that would be, this is called the eigenvector. I'm sorry, the x is called the eigenvector of A, and the lambda here is called the eigenvalue. And again, this is the eigenvector of A. It'll make some more sense as we do them, but let's go ahead and get started with our exercises from 7.1. And we are going to first start verifying eigenvalues and eigenvectors. They're just going to give us some things here. So we're going to get matrix A is 2, 0, 0, -2. And they want us to verify that if lambda 1 is 2, that makes an eigenvector of 1, 0, and if lambda is 2, or lambda 2 is -2, that gives us an eigenvector of 0, 1 that's associated with that. So how can we prove that? Well, we can take A times x1 is 2, 0, 0, -2 times 1, 0, and that's going to be 2 plus 0 is 2, and then 0 plus 0 is 0, and I can pull out my 2, and that's 1, 0. So that proves to me that 2 is the eigenvalue and 1, 0 is the eigenvector here. And we can take A times x2 and get 2, 0, 0, -2. And we have 0, 1. That is 0, -2, which is -2 times 0, 1, which is an eigenvalue of -2 and an eigenvector of 0, 1, just like we were told we should have. Let's try that now with a 3 by 3 instead of just a 2 by 2 with number 3. So A is equal to 2, 3, 1, 0, -1, 2, 0, 0, 3. And they want us to know that lambda 1 is equal to 2, and that's associated with the eigenvector 1 of 1, 0, 0. And lambda 2 is equal to -1, and that makes the second eigenvector here 1, -1, 0, and lambda 3 is 3, making the third eigenvector here 5, 1, 2. So A x1 is 2, 3, 1, 0, negative 1, 2, 0, 0, 3 times 1, 0, 0 is 2, 0, 0 is 2 times 1, 0, 0. So eigenvalue 2, eigenvector 1, 0, 0. AX2, 2, 3, 1, 0, negative 1, 2, 0, 0, 3 times 1, negative 1, 0. So that is 2 minus 3 is negative 1. Negative 1 times negative 1 is 1. And this is 0. And that equals to 1 times negative, oops, I'm sorry, equals negative 1 times negative 1, 1, 0, that this is the opposite of my original vector. So I have an eigenvalue of negative 1 and eigenvector of 1, negative 1, 0. 1, negative 1, 0. So AX3 is 2, 3, 1, 0, negative 1, 2, 0, 0, 3 times 5, 1, 2. So 10 and 3 is 13 and 2 is 15. And then negative 1 and 4, that's 3. And 3 times 2 is 6. So that looks like a common factor of 3 to come out. 5, 1, 2. 5, 1, 2 is what I started off with. Eigenvalue of 3, eigenvector of 5, 1, 2. Let's go ahead and look at number 9 now. And we're determining eigenvectors. So determine whether the vector given is an eigenvector of A. So A is equal to 7, 2, 2, 4, and A asks about the vector 1, 2. So I'm going to take AX is 7, 2, 2, 4, 1, 2 is equal to 7 plus 4, 2 plus 8, that's 11, 10, which in no way has a factor that comes out that leaves me with 1, 2. So this is not equal to lambda times 1, 2. So X is not an eigenvector of A. Let's look at part B. Second vector we're testing is 2, 1. So 7, 2, 2, 4, 2, 1. That's 14 plus 2. That's 4 plus 4. That's 16 and 8. That's 8. That's 2, 1. So yes, X is an eigenvector of A with a corresponding eigenvalue of 8. Even though we weren't asked for that, Since we have both pieces, might as well give both pieces. C, x is equal to 1, -2. So 7, 2, 2, 4, 1, -2. That's 7 minus 4. That's 2 minus 8. That's 3, -6. And that is 3, 1, -2. So yes, x is an eigenvector of A with a corresponding eigenvalue of 3. Right? Part D equals -1, 0. So 7, 2, 2, 4. -1, 0 is -7, -2, which is not equal to lambda times -1, 0. So x is not an eigenvector of A. Let's look now at number 11. Very similar problem. 11 says A is equal to -1, -1, 1, -2, 0, -2, 3, -3, 1. We want to test if x bar equals 2, -4, 6 is an eigenvector. So -1, -1, 1, -2, 0, -2, 3, -3, 1, 2, -4, 6 is -2 plus 4 plus 6, -4 plus 0 minus 12, 6 plus 12 plus 6 gives me 8, -16, and 24, and try to pull out a 4 here, gives me 2, -4, 6, so yes, x bar is an eigenvector of A with a corresponding eigenvalue of 4. Part B, 206, -1, 1, -2, 0, -2, 3, -3, 1, 2, 0, 6. That's going to be -2 plus 6, -4 minus 12, 6 plus 6 is 4, -16, And 12, can that be written? No, that can't be written as lambda times 2, 0, 6. If I tried to pull out the 2 here from the 4 to make it 2, that would leave a -8, not a 0. These two components would be right, but the middle one would be wrong. So x bar is not an eigenvector of A. All right, let's look at part C. C asks me about the vector 2, 2, 0. So I want -1, -1, 1, -2, 0, -2, 3, -3, 1. I want 2, 2, 0. So that is -2 and -2 is -4. -2, and then 6 minus 6, that's 0. Let's pull out a -2. Leaves me with 2. Let's see here. This is -4. How are they getting that? Oh, I just can't multiply. -2 times 2 is -4. So this is 2, 2, 0. And so yes, this bar is an eigenvector of A with a corresponding eigenvalue of -2. And then last one here, D x bar equals -1, 0, 1. It's me -1, -1, 1, 2, 0, -2, 3, -3, 1, -1, 0, 1 is 1 plus 1, 2 minus 2, -2. And -3 plus 1. So that is 2, 0, -2. And I'm going to pull out a -2 times -1, 0, 1. So yes, x bar is an eigenvector of A with a corresponding eigenvalue of -2. Okay. Look at number 13 next. And this is a different problem set, so let me tell you what the instructions are here. So 13 says, finding eigenspaces in R2 geometrically. We've just got one of these to do. You can look at the example, but we're basically trying to find if these things, if these transformations represent reflections across the x-axis, y-axis, or origin. So this here, we've left x alone, but we've changed the value of y. So this is a reflection across the x-axis. Here is what that transformation has to do with. Just prove that to you, that if I have ax equals 1, 0, 0, negative 1, xy, that this is equal to x negative y, like so, which is a reflection across the x-axis. Then we're going to look at the anything that is on the x-axis. So for first eigenvector here is anything on the x-axis. So that is an eigenvector there with an eigenvalue of 1. And then let's look at anything on the y-axis, like so. And we're going to pull out a negative 1 from that. So that makes lambda 2 equal to negative 1. So the eigenvalues are lambda 1 equals 1 and lambda 2 equals to negative 1, and the corresponding eigenvectors are the x-axis and y-axis respectively. That's the only one of those to do. That was number 13. Move on to a different problem set now with number 15. It asks us to find the characteristic equation, eigenvalues, and eigenvectors. So this is more what you're typically going to be doing. This is a important tool to be able to use in higher level mathematics, especially higher level differential equations classes. So if you want to see an application of this, it's not used a whole lot in our 200 level differential equations class, but there is an application in a 400 level differential equations class. Once I finish this video, in the near future, I will be going back to the differential equations playlist and adding a bonus, some bonus content, and it will be discussing solving systems of differential equations, and that involves eigenvalues and eigenvectors a whole lot. So what we're going to find now is for the characteristic equation, and I'll just write this the first time, we want lambda I minus A. So what I want is everything along this diagonal. I want lambda minus that value along the main diagonal. Everything else, I just want to change the sign of it. And I want that determinant to be equal to 0. That's my characteristic equation, is that this determinant needs to be equal to 0. So that's lambda minus 6 times lambda minus 1. 3 times 2 is 6 equals 0. Lambda squared minus lambda minus 6 lambda is minus 7 lambda, plus 6 minus 6 equals 0. 6 minus 6 is 0. Common factor of lambda. Lambda minus 7 equals 0. So lambda 1 equals 0. Or lambda 2 is equal to 7. For lambda 1 equals 0, coming back to this form right here, 0 minus 6 is negative 6. 3, 2, 0 minus 1 is negative 1. I'm going to augment that with the 0 matrix to find where my zeros are. This is always going to give me a row of zeros, that one of these rows, at least one of the rows, will be a constant multiple of the other row. So when I RREF this, I'm going to get 2, negative 1, 0, 0, 0, 0. So that tells me that 2 x1 is equal to x2. So if x2 is 2 times x1, I can make x1 equal to t, and x2 is going to be 2t, and that makes all my eigenvectors in the form of t, 2t, but I want to get the simplest form of that I can, since the t's will be taken care of by the lambdas. So I want to pull the t out and say that this is going to be 1, 2 for my eigenvector. Okay. And then for lambda 2 is equal to 7, then I'm going to have 7 minus 6, 3, 2, 7 minus 1, augment 0, 0. That's 1, 3, 2, 6, 0, 0. When I reduce that, I get 1, 3, 0, 0. And so that means that x1 is equal to negative 3 x2. x2 is equal to t. So I'm going to call this negative 3t. And so I look at my coefficients here, negative 3, 1 for my eigenvector. Let's go ahead and look at number 19 here. We have 1, negative 3 halves, 1 half, negative 1. So writing my characteristic equation here, I have lambda minus 1, 3 halves, negative 1 half, lambda plus 1 equals 0, lambda minus 1, lambda plus 1 minus 3/4 equals 0, lambda squared minus 1 minus, this is minus a negative, so that's plus 3/4 equals 0, lambda squared minus 1/4 equals 0, lambda plus a half, lambda minus a half equals 0, lambda 1 equals negative a half, lambda 2 equals positive a half. When lambda 1 equals negative 1/2, then we have negative 3/2, 3/2, negative 1/2, 1/2, 0, 0 is going to yield -1, -1, 0, 0, 0, 0, which makes x1 equal to x2. Doesn't really matter, they'll both be t. And we have a eigenvector of 1, 1. When lambda 2 equals positive 1/2, we have negative 1/2, 3/2, negative 1/2, 3/2, 0, 0. So that is going to be 1, -3. Just multiplying through by -2 here on this top row. That was identical, so that's 0, 0, 0, meaning that x1 is equal to 3x2. x2 is going to be my t, so this is 3t, giving me an eigenvector of 3, 1. Let's jump ahead now to number 21. That says that we have the matrix A, 2, -2, 3, 0, 3, -2, 0, -1, 2. And we want to find the characteristic equation, so that's lambda minus 2, 2, -3, 0, lambda minus 3, 2, 0, 1, lambda minus 2 equals 0. Expanding on column 1 here, lambda minus 2, and then determinant of lambda minus 3, 2, 1, lambda minus 2. Why did I choose that? Because there's 2 zeros there. So that makes my life easiest. Lambda minus 2 times lambda minus 3, lambda minus 2 minus 2. So this is lambda minus 2 times lambda squared minus 3 minus 2 is minus 5 lambda plus 6 minus 2 is lambda minus 2 times lambda squared minus 5 lambda plus 4 is lambda minus 2 times lambda minus 1 times lambda minus 4. These are all equal to 0. So lambda 1 equals 2, lambda 2 equals to 1, lambda 3 is equal to 4. So we'll have 3 cases here to solve. So for lambda 1 is equal to 2, that's going to be 2 minus 2 is 0, 2, negative 3, and the 0 over here, 0, 2 minus 3 is negative 1, 2, 0, 1, 2 minus 2 is 0. So when we reduce row echelon form that, we get 0, 1, 0, 0, 0, 1, 0, 0, 0. This tells me that x2 is equal to 0 and x3 is equal to 0, but x1 is free variable that's t. So 1, 0, 0 is my eigenvector. I'm going to pull out my factor of t. For lambda 2 is equal to 1, we have 1 minus 2 is negative 1, 2, negative 3, 0, 0, 1 minus 3 is negative 2, 2, 0, 1, 1 minus 2 is negative 1. Those are all zeros on the right-hand side. RREF that, and I get that one, 0, 1, 0, 1, negative 1, 0, 0, 0. So that tells me that x1 is equal to a negative x3, x2 is equal to x3, x3 is my t, so this is a negative t, and this is a t, so negative 1, 1, 1 is my eigenvector here. And then for lambda 3 is equal to 4, then we have 4 minus 2 is 2, 2, negative 3, 0, 4 minus 3 is 1, 2, 0, 1, 4 minus 2 is 2, 0, 0, 0. We're going to RREF this. RREF. And we get 1, 0, negative 7 halves, 0, 1, 2, 0, 0, 0. So this is x1 equals 7 halves x3. X2 is a negative 2. X3 is t. But I really want to choose my t here to be 2 so that everything comes out to be integers. Negative 2 times 2 is negative 4. 7 halves times 2 is 7. I just wanted to choose something that would get rid of that fraction for my eigenvector here, 7, negative 4, 2. Let's go ahead and look at 25. 25 is 0, negative 3, 5, -4, 4, -10, 0, 0, 4. And that makes my characteristic equation lambda minus 0 is lambda, 3, -5, 4, lambda minus 4, positive 10, 0, 0, lambda minus 4. I'm going to expand on this bottom row here with lambda minus 4 is positive. Going to have lambda 3, 4, lambda minus 4 is equal to lambda minus 4 times lambda squared minus 4 lambda minus 12 equals 0. That's lambda minus 4 times lambda minus 6 times lambda plus 2 equals 0. So lambda 1 equals 4. Lambda 2 equals 6. Lambda 3 equals -2. For lambda 1 equals to 4, I have 4, 3, -5, 4, 0, 10, 0, 0, 0, 0, 0, 0. Going to RREF that. I'm going to get 1, 0, 5 halves, 0, 0, 1, -5, 0, 0, 0, 0, 0. And that tells me that my x1 is -5 halves x3, and that x2 is 5 x3, and that my x3 is t. So I want to choose t to be 2 here so that I get integer values of -5, 10, and 2. Let's look now at lambda 2. So for lambda 2 equals to 6, I have 6, 3, -5, 0, 4, 6 minus 4 is 2, 10, 0, 0, 2. I'm going to RREF this, and that's going to give me 1, 1/2, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So that tells me that x1 equals -1/2 x2, x3 equals 0, x2 is my t, so this is -1/2 t. For some reason, they don't want to, they want to let t be -2 in this case. So that's fine. You could let it be 2 and it would also be a correct answer. The book goes with t being -2 and getting a eigenvector of 1, -2, 0. And now we want to let lambda 3 be equal to -2. So I'm going to do that. I have -2, 3, -5, 4. -2 minus 4 is -6. 10, 0, 0, -2 minus 4 is -6. Augment this with the 0 matrix. RREF this, and we're going to get 1, negative 3 halves, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, which means that x1 is 3 halves x2, x3 is 0, x2 is t. We're going to let t be 2 this time. So we have 3, 2, 0 for our eigenvector. Moving on to number 29. Number 29 asks us to find eigenvalues using technology. I'm just going to continue to do them by hand since I don't have a software program to do this for me. It's pretty straightforward on this one. -4, 5, -2, 3. If you do have a software program that can do it for you, go ahead and practice doing that. This is just going to be the characteristic equation. Lambda plus 4, -5, 2, lambda minus 3. Determinant of that equals 0. Lambda plus 4 times lambda minus 3 minus a -10 is plus 10 equals 0. So this is lambda squared. -3 plus 4 is plus 1 lambda minus 12 plus 10 equals 0. So lambda squared plus lambda minus 2 equals 0. Lambda plus 2 times lambda minus 1 equals 0, giving me lambda 1 as -2 and lambda 2 as +1. So all they wanted you to do was find those lambda values, those eigenvalues. So we're ready to move on now to number 35. 35 is also in the same section where we just want to find our eigenvalues. It's a little bit harder to find them here. We have 3, then we have -1/2, then we have 5, then we have -1/3, and then -1/6, and then we have -1/4, and 0, 0, 4. Okay, so now we would like to write our characteristic equation, lambda minus 3, +1/2, -5, +1/3, lambda plus 1/6, +1/4, 0, 0, lambda minus 4 equals 0. I'm going to expand on this bottom row that has the zeros, lambda minus 4. I'm going to get rid of that. This is lambda minus 3, +1/2, +1/3, lambda plus 1/6 equals 0. Lambda minus 4, and this is lambda minus 3, lambda plus 1/6 minus 1/6 is equal to 0. So this is lambda minus 4, lambda squared plus 1/6 lambda minus 3 lambda minus 1/2 minus 1/6 is equal to 0. Lambda minus 4, lambda squared. So this is 18 over 6. So 1 minus 18 over 6, that's minus 17 over 6 lambda. And then -3/6 minus 1/6 is -4/6. So that's minus 2/3 is equal to 0. And I have a sneaking suspicion that we have a quadratic equation here that we're going to need the quadratic formula for. Let's look at that in just a second. Right, so I would like to go ahead and pull the 1/6 out here. It's not going to change my answer. 6 lambda squared minus 17 lambda minus 4 equals 0. And let's go ahead and use the quadratic formula to find, we know that lambda 1 is equal to 4, but over here, lambda equals negative b plus or minus the square root of b squared. 17 squared is 289 minus 4ac. So 4 times 6 is 24 times negative 4. That's going to give me positive 96 all over 2 times a. That's 12. So my lambda is equal to 17 plus or minus the square root of 289 plus 96 is 385. No perfect squares as factors inside of that, meaning that lambda 2 is equal to 17 plus root 385 over 12, and lambda 3 is equal to 17 minus root 385 divided by 12. This is a lambda. Okay, so that is it for this video, and that is it for our linear algebra topics. Again, the main reason for eigenvalues and eigenvectors that I can tell you right now is to solve systems of differential equations. They have other applications in engineering for sure, and other fields of mathematics and applied mathematics. I can't tell you all the places you would use them, but they're very useful in those applications. So look forward to using them to help you solve some very complicated things and getting your solutions, especially there's multiple solutions sometimes in the eigenvalues, and eigenvectors help you form those multiple possible solutions that you could have to your equation. Hope you enjoyed this. Good luck with whatever your next topic, your next course may be, and have a good day.